If you're interested in learning about blockchain, this is the course for you. Patrick Collins is a veteran software engineer and longtime finance industry developer. Be sure to leave a comment with something you learned from this course.
Welcome to the ultimate Solidity, smart contract, and blockchain developer course, JavaScript edition. We recently did a version of this video in Python that has over 2 million views right now, making it the most watched smart contract tutorial on the planet. We've learned a ton from doing that first course, and if you love the Python language, definitely be sure to check that one out. We've taken all the learnings we've got from making that first course, wrapped it up, and put it into this JavaScript video for you. If you're looking to get started in Web3, blockchain, smart contracts, or any of these terms, this is the course for you. And it's for anybody and everybody, no matter your experience level in programming or in blockchain. Ideally, you know a little bit of JavaScript before starting this, but if you don't, no worries, we will help you along the way. And in case you do want to learn a little bit of JavaScript before starting here, there are some fantastic courses on Free Code Camp to learn more, but you absolutely don't have to. And really, any experience with any object-oriented programming language will work great. So if you're brand new to coding, or if you're brand new to blockchain, this is exactly where you should be. And if you already know a lot about blockchain or coding, this course will give you even more deep fundamentals on the space. So welcome to the edge of the rabbit hole. So for those of you who don't know, my name is Patrick Collins. I'm a smart contract engineer, developer advocate on the Chainlink protocol, and I live and breathe smart contracts. I also make YouTube videos on my own channel, Medium, Twitter threads, and more, teaching people about smart contracts, about coding, and about this new technology. I love helping developers learn, grow, and learn about this new advent that's blockchain and smart contracts. And I'll be taking you on your journey to becoming a blockchain expert and wizard of the smart contract developing world. And even if you don't want to become a developer, the first section, our blockchain basics, will give you a lot of fundamental knowledge about how blockchains and smart contracts even work. I am so excited for you to be here, and I hope you enjoy the journey. This is a data dump, passion, educational project of everything I've learned working in this space. And I am 100% certain that if you follow along, you'll come out the other side of this armed with the knowledge to be a positive force in this incredible industry. Solidity and smart contract developers are massively in demand, with an average salary of being around $145,000 a year. There is massive economic opportunity from learning this course. And this technology has the ability to revolutionize everything that we interact with. And you can be one of the pioneers ushering in this new age. In our courses, we already have a track record of giving people these educational needs and sending them into their careers in the blockchain and smart contract space. And we are going to give you all of the cutting edge tools and how to use them, including working with things like DeFi, NFTs, DAOs, ERC20s, upgradable smart contracts, and more. We're going to teach you the skills necessary to build DeFi applications like Aave, Synthetics, and Compound, billion-dollar decentralized applications, or massively successful NFT projects like CryptoPunks or Bored Apes, DAOs like MakerDAO or DeveloperDAO, and any of the amazing things you've seen in the cryptocurrency world. In learning these skills, you will have all these economic opportunities at your fingertips and the ability to be a pioneer in completely changing the way we interact with each other in a fundamental way. Building decentralized smart contract applications is building a world that's more accountable, a world with unbreakable promises, a faster, more efficient, financially free world, a collaborative community combining the prowess of philosophy and technology into a new system. We'll learn more about the purpose and the value of smart contracts and decentralized applications in lesson 1 of this course, and why they're so exciting. Finish this course and you'll be ready. So again, I want to give a major thank you and a major kudos to you because you've taken the first step to enter this realm. So welcome to Web3, welcome to the blockchain, welcome to smart contracts, and I'll see you at the bottom of the rabbit hole. So let's jump into some best practices for this course so that you can learn most effectively and learn with this course as best you can. You do not want to skip this part. It'll help you solve 80% of your issues. Now, while going through this course, be 100% certain to follow along with the GitHub repository associated with this course. We have a link in the description of this video for you to absolutely click on, follow along, have open in a tab as you're doing this, because it has all the code samples, timestamps, a community to interact with, and more. It is going to be your Bible for watching this course. And yes, we have a discussions tab. This discussions tab is a place where you can ask questions, engage with other developers who are going through this course as well, get some help, and etc. Be sure to say hello and meet other like-minded individuals like yourselves. Now, blockchain and smart contracts move really quickly, and things are constantly being updated. So to make sure you're always up to date with the latest, when I open up some documentation, try to open up the documentation for yourself as well, and maybe even have the code sample next to you. And as you're writing code, be sure to refer back to make sure that you are keeping pace and that you have the most up-to-date samples. Sometimes technology might change and there might be a way to do something a little bit better. So we have this file called chronological updates. Be sure that this is the first place to check when you run into an issue to see if maybe something was updated that you missed. It'll be chronologically ordered so it's easier to find updates. Basically, this is to say, always refer back to the GitHub repo first. And if you do find a mistake or something isn't working the way you expected, jump into the conversation, leave a discussion, leave an issue, ask questions here. Take breaks. I cannot tell you how many people tried rushing through our entire first course in one sitting and didn't retain as much information. Your brain remembers information much better if you take breaks. So every 25 minutes or half an hour, maybe take a 5-minute walk. And then every 2 hours, take a much longer break. And if you really want to make sure something drills in, try to go back and reflect on what you did from the lesson prior before continuing to the next lesson. And at the same time though, learn at your own speed. There is no right speed for this course. If it takes you a day, a week, a month, or even a year, it doesn't matter. Learn at the pace that's right for you. You can change the speed at which I talk using the little gear icon in the YouTube video. If I'm talking way too fast for you, you can slow me down. And at the same time, if I'm talking too slow, you can speed me up. You also don't even have to go in order. You can bounce around topic to topic. If you don't want to learn full stack, you can skip the full stack stuff. If you don't want to learn coding, well, you can skip the coding stuff. If you only want to go to the advanced stuff, go to the advanced stuff. You are highly encouraged to pause, come back, and ask questions. The blockchain and smart contract world is incredibly collaborative. So be sure to use tools like the discussions tab of our GitHub repository, asking questions on Stack Overflow and Ethereum Stack Exchange and tagging relative technologies, making issues on different GitHub repositories that you're working with, jumping into Discords, Reddit, Twitter, and any other place that these communities and technologies are congregating. And the reason I'm putting so much emphasis on these community aspects is that becoming a Solidity and blockchain engineer is so much more than just the Solidity part. Being comfortable with all the tools in this space, including the ones to get help and to give help, are essential to being successful here. Networking is massive and it makes it a ton of fun. As you continue your journey and you get more advanced and you're looking for places to meet other developers, hackathons are one of the best places to connect with other engineers. The Chainlink hackathons, ETH Global hackathons, and DevFolio hackathons are 3 great hackathon suites to connect. And no matter where you are in your journey, they're great places to flex what you've learned. All right, so those are some of the best practices for this course. You're standing at the edge of the rabbit hole, looking down, peering into the world of Web3 and smart contracts and blockchain. If you're like me, once you jump in, you'll want to keep going further. Let's begin our journey into the world of smart contracts. And it all starts with the blockchain basics. Now, I know you're excited to get coding, but before we jump in, we want to learn some of the fundamentals of blockchains and smart contracts. Understanding these ideologies and these basics are so important because it'll dictate how you architect your decentralized applications. Learning the basics of blockchain and Solidity is critical. But if you already know the basics of a blockchain, feel free to jump into lesson 2. Now, since you're here, you've probably heard of Bitcoin before. Bitcoin was one of the first protocols to use this revolutionary technology called blockchain. The Bitcoin white paper was created by the pseudo-anonymous Satoshi Nakamoto, and it outlined how Bitcoin could make peer-to-peer transactions in a decentralized network. This network was powered by cryptography and decentrality, and it allowed people to engage in censorship-resistant finance in a decentralized manner. Due to its features, which we'll talk about in a little bit, people took to this as a superior digital store of value, a better store of value over something like gold, for example. And that's why you'll also hear people commonly refer to it as a digital gold. Similar to gold, there's a scarce amount or a set amount of Bitcoin available on the planet. Only so much that you can buy and sell. You can read more about the original vision in the white paper. We have a link to the white paper in the GitHub repo associated with this course. Now, this was an insane breakthrough. And in a little bit, we're going to learn exactly how this is all possible and how this actually works under the hood. Some people, though, saw this technology and wanted to take it a little bit farther and do even more with this blockchain technology. And a few years later, a man named Vitalik Buterin released a white paper for a new protocol named Ethereum, which used this same blockchain infrastructure with an additional feature. And in 2015, him and a number of other co-founders released the project Ethereum, where people could not only make decentralized transactions, but decentralized agreements, decentralized organizations, and all these other ways to interact with each other without a centralized intermediary or centralized governing force. Basically, their idea was to take this thing that made Bitcoin so great and add decentralized agreements to it, or smart contracts. And in fact, technically, these smart contracts weren't even really a new idea. Back in 1994, a man named Nick Szabo had actually originally come up with the idea. Smart contracts are a set of instructions executed in a decentralized autonomous way without the need for a third party or centralized body to run them. And they come to life on these blockchains or these smart contract platforms like Ethereum. And it's these smart contracts that are going to be the core thing that we're going to be working on in this course and that we're going to be developing. You can think of smart contracts in the same way you think of traditional contracts or traditional agreements. They're just a set of instructions between parties. Except instead of written on pen and paper or typed up in Microsoft Word, they are written in code and embodied on these decentralized blockchain platforms. And that's also where they're executed, instead of being executed by the 2 parties or 3 parties or however many parties that are involved. This removes this centralized issue that we'll talk about more in a bit. This is one of the main differentiators between the Ethereum protocol and the Bitcoin protocol. It's these smart contracts. Now, technically, Bitcoin does have smart contracts, but they're intentionally Turing incomplete, which means they don't have all the functionality that a programming language would give them. This was an intentional move by Bitcoin developers. Bitcoin developers viewed Bitcoin as a store of value, versus Ethereum developers viewed Ethereum as both a store of value and a utility to facilitate these decentralized agreements. Now, these smart contracts on blockchains alone are absolutely incredible. However, they do come with a huge issue. If we want these digital agreements to replace the agreements in our everyday lives, they probably are going to need data from the real world. Blockchains by themselves actually can't interact with and can't read or listen to data from the real world. This is what's known as the Oracle problem. These blockchains are deterministic systems, and they're deterministic on purpose. And we'll learn more about how that works in the sessions to come. So everything that happens with them happens in their little world. But if they're going to be these agreements, they need external data and they need external computation. And this is where oracles come into play. Oracles are any device that delivers data to these decentralized blockchain or runs external computation. However, if we want our applications to stay truly decentralized, we can't work with a single oracle or a single data provider or a single source that's running these external computations. So we need a decentralized Oracle network similar to our decentralized blockchain network. Your on-chain logic will be decentralized, but you also need your off-chain data and computation to be decentralized. Combining this on-chain decentralized logic with this off-chain decentralized data and decentralized computation gives rise to something called hybrid smart contracts. And most of the biggest protocols that we interact with today are some type of hybrid smart contract, or interact with hybrid smart contracts to some extent. This is where the protocol Chainlink comes into play. It is a modular, decentralized Oracle network that can both bring external data and external computation into our smart contracts to make sure they're decentralized end-to-end while giving them the feature richness that we need for our agreements. Chainlink allows for us to get data, do upkeeps, get random numbers, or really customize our smart contracts in any meaningful way. Now, throughout the course, we're going to use the terminology smart contract. However, whenever we say smart contract, we're often using it a little interchangeably with hybrid smart contracts. But just know that when we say hybrid smart contract, we're talking specifically about smart contracts that have some type of off-chain component. Now, since Ethereum's release, a number of different blockchains or smart contract platforms have come to light, such as Avalanche, Polygon, Phantom, Harmony, and more. For the majority of this course, we're going to be assuming that we're going to be deploying to the Ethereum network. However, everything that we learn here is going to be applicable to the vast majority of the blockchains out there, like Polygon, Avalanche, Phantom, Harmony, etc. And understanding everything from Ethereum fundamentals will give you the skills that you need to switch chains very easily with literally one line of code. So don't worry about learning a specific tool or with a specific chain, because most of them work together seamlessly. Now, there are a couple of smart contract platforms that don't use Solidity, but still learning the fundamentals here will make you much better at those as well. And Ethereum by far has the most value locked and is the most used blockchain and smart contract platform out there. You'll also hear those two terms used a little bit interchangeably as well. Sometimes I'll say smart contract platform, sometimes I'll say blockchain. They kind of mean the same thing. Obviously, blockchains could mean store of value and smart contract platform, but you get the idea. Similarly, Chainlink is the most popular and powerful decentralized Oracle network, is the one that we're going to be focusing on for this course as well. Chainlink is also blockchain agnostic, so it'll work on Ethereum, Avalanche, Polygon, Solana, Terra, or really any other blockchain out there. Now, throughout this course, you'll hear the term DApp, or decentralized protocol, or smart contract protocol, or decentralized application, and they all kind of mean the same thing. A decentralized application is usually the combination of many smart contracts. And when we get into Solidity, you'll see what a singular smart contract really looks like. And like I said, learning all these core fundamentals will make you a better Solidity and a better smart contract developer. You'll also hear the term Web3 a lot in this video and in the industry. Web3 is the idea that blockchains and smart contracts are the next iteration of the web. Web 1 being this permissionless open source world with static content. Web 2 being the permissioned web with dynamic content. But all the agreements and logic runs off of centralized servers where they control your information. And then Web 3 comes back to the permissionless web, but once again with dynamic content. And instead of centralized servers running your logic, decentralized networks run the logic, creating these censorship-resistant agreements that these smart contracts enable. It is also generally accompanied by the idea that the users own the protocols that they work with, and it's an ownership economy. You'll see what I mean later in this course. Now, we've talked a lot about the history and about the high level of these protocols and of these smart contracts and what they can do. But what do these smart contracts really mean? What is it when I say trust minimized agreements or unbreakable promises? What is the real value add of these smart contracts? Before we look under the hood and take a peek at how this all works from a technical standpoint, let's learn what all the value of this is. What is the purpose of us building all these technologies, of you taking this course? What problem does this technology solve? In my mind, a technology is really only as good as the problem that it solves. If it doesn't solve a problem, then why bother? Smart contracts, blockchain, Web3, cryptocurrencies, those are all just different words that encapsulate the idea of what we're doing in such a unique paradigm. I think the easiest way to sum up what these smart contracts do is that they create trust minimized agreements. And if you might be scratching your head to that, a much easier way to think about it is just they give rise to unbreakable promises. Yes, you heard that right. Unbreakable agreements and promises. Additionally, they give rise to speed, efficiency, and transparency, and a number of other things. I made a video pretty recently about exactly this. So let's dive in and take a listen to the purpose, the undeniable value of smart contracts. Cryptocurrencies fundamentally re-landscape markets and agreements as we know them. Unfortunately, you've probably only been bombarded with people screaming about NFTs and money. Now, some of the memes are fun, but let's forget the bullshit and get down to the essence of this space. If you're already in Web3, this is the video to send to your friends to explain why you're so excited about this space and explain why we're here. And then if you're not into crypto, you've come to the right place. And yes, there are fun memes and markets and there's some money stuff and there are all these things. But outside of all that, the purpose of blockchains relates to the age-old elementary school unbreakable promise, the pinky swear. Let's get froggy. Nearly everything you do in life is the result of an agreement or a contract. Your chair was the result of an agreement to buy and sell lumber, to assemble and sell the chair to a retailer on Amazon. Then you made an agreement to buy the chair for $40. The lights in your house are powered by electricity, which is an agreement from you and the electric company. You agree to pay them. In return, they'll keep the lights on. The electricity that they generate is agreements between them and engineers who built turbines to generate the electricity. With insurance, you agree to pay some amount of money to them every month, and in return, they will do nothing. They'll cover your medical bills. Almost everything you do and everything you interact with is the result of some form of agreement or contract in some aspect. Now, agreements and contracts can feel kind of abstract and boring to really grasp onto. So to simplify, we can also refer to them as promises. When you get an oil change, they're promising that they will faithfully change your oil in exchange for money. When you put money in the bank, they promise to keep it safe in exchange for them to use your money to give out loans. When you buy a lottery ticket, the lottery promises to give you a fair chance at winning a ton of money in exchange for you buying the ticket. Whenever you make one of these agreements, in a way, you're asking them to pinky swear to not screw you over and to treat you fairly. But this doesn't always happen. Let's look at a real world example of someone breaking the pinky swear. Back in the 80s and 90s, McDonald's ran a promotion for people to win money by collecting McDonald's Monopoly game cards. The idea was simple. You buy McDonald's, and in return, you get a chance to win $1 million. You can imagine McDonald's literally going, "Hey everybody, I promise if you buy our McFood and McNuggets, we'll give you a fair chance of winning this money. Woo!"
But they ended up breaking this promise.
Instead of having a fair chance of winning, your chance was in fact zero. In the mid-90s, between $13 and $24 million went into the pockets of not people playing the game honestly, but a group of corrupt insiders who had rigged the game. Meaning that when you played the McDonald's Monopoly game, you were buying into a set of lies and promises that were 100% always going to be broken. And the thing is, it doesn't really matter if this was McDonald's fault or not. They were the ones making the promises that they ultimately could not keep. Another way you could think about it is that that's $24 million that they essentially stole from you and I. Now, if this system was deployed on a blockchain with something called a smart contract, it would have been impossible to defraud this $24 million due to smart contracts being immutable, decentralized, and transparent. But I'll get back to that in a minute. In all the agreements and contracts we make, imagine making a pinky swear with a 10-year-old and imagining how that agreement would hold up. "Hey buddy, could you please keep my money safe? You can play with it if you like, but just please have it when I come back." Immediately, you might get that worrying feeling in your chest. Something might go wrong, that this 10-year-old might lose your money. You might be thinking, how could I trust them? Will they break their promise? And this feeling of, I can't breathe because of untrustworthy situations happens to us all the time. Can I trust this used car salesperson to give me a good car? Can I trust this tag that says machine washable, or will it make my shirt shrink? Will my insurance provider break their promise of covering my medical bills when I get hit by a bus?
When Patrick promises he'll go on a hike with me, will he actually?
Yes, Becca, I actually will. The issue with our current agreements and contracts is we have to trust the people who are making them to do the right thing. However, often they're actually incentivized to not do the right thing. Insurance doesn't want to pay out money. Sometimes salespeople just want to get the shit off their shelves. And with my girlfriend, I promised to go on a hike, but I hate hikes. Where else has this happened? Now you might be thinking, okay, Patrick, this seems cool, but like, where has this actually affected me? Well, the McDonald's lottery that we just spoke about above. During the Great Depression, with the run of the banks promised to keep our money safe, and that when we went back to go get it, they would actually have the money there. And well and behold, there were times that they didn't have the money there. Just last year, Robinhood painted this amazing picture. Come use our application. We will give you access to the markets. We promise we will give you, a retail investor, a fair chance of interacting with the world of finance. Psych! But not this asset, this asset, this asset, or this asset. The 2008 financial crisis. Remember that? Shady deals behind closed doors combined with lies about financial product brought the world to its economic knees.
How are you f***ing us?
Hyperinflation in Zimbabwe. Hyperinflation in Brazil. Theranos. History is a relentless lesson of trustworthy entities being notorious promise breakers. And we finally have a way to fix it with smart contracts. Now, before I jump into smart contracts, a lot of people might be thinking, hey, cool and all. However, we have systems in place to protect against a lot of these things, which is true and which is great. And that is a very helpful step forward. But these systems often break. The ones in 2008 definitely didn't work. The ones with the Robinhood crisis definitely didn't work. And even if these systems apply and you go to court to try to work them out, maybe you're in court for years before you actually see a resolution. And by that time, what you needed the money for is long gone. So what is this technology? What is this tool that can fix this fundamental problem in our agreements today? This tool is smart contracts, and this tool is what the blockchain was built for. Now, I'm going to give you a quick overview of what a smart contract is. However, I'm leaving some links in the description for more in-depth explanations. But the basics of them is a smart contract is an agreement, a contract, or a set of instructions deployed on a decentralized blockchain. And once the contract or set of instructions is deployed, it cannot be altered, it automatically executes, and everyone can see the terms of the agreement. The real basics of it is that the code is executed by a decentralized collective, like a group of people, but a group of people running a certain software. This means that no one person or entity can actually alter any of these agreements or change the terms of the arrangement. In these traditional agreements, whoever owns the contract, whoever owns the execution of the contract can flip a switch and say, we're not going to do that anymore. In smart contracts, in Web3, in blockchain, you no longer can do that. Typically, these smart contracts are on a decentralized blockchain and used in combination with a decentralized Oracle network to get the real world assets and information. And if these words sound like I'm conjuring up a magic spell, well, again, check the links in the description if you want to learn more about the technical implications. If you're not a technical person and you're not interested in getting to the nitty-gritty, you can kind of think of it like HTTPS. I bet the vast majority of you don't even know what HTTPS stands for, and yet you use it every single day whenever you log onto the internet. So how does this fix the McDonald's monopoly issue? In its traditional form, the lottery was executed behind closed doors. Somebody operated and owned the code and the contracts and the agreements that ran the lottery, and they had the power to alter it, and nobody other than the people internal on the lottery could audit this altering happening. Now, if the code for this lottery was deployed onto a blockchain, every time a hacker attempted to alter it, everyone would be notified. Not only that, but you couldn't even alter it because the terms of a smart contract cannot be altered once deployed. Combine that smart contract with a Chainlink VRF Oracle to get a verifiably random number, and presto, you now have a perfectly decentralized, unalterable agreement that is impossible to hack, commit fraud, or manipulate. We have just saved the public between $13 million and $24 million just by fixing the issue of trust. How does this fix Robinhood? Well, the problem with Robinhood is already fixed, right? Again, the problem is that there's a centralized body that can flip a switch at any time and say, yeah, you can't access these markets anymore. We're breaking our promise of actually giving you access to the markets. This is already fixed with something called decentralized exchanges, and these exist today. One of these exchanges is one called Uniswap. You can swap ERC20 tokens, which are kind of the equivalent of stocks, but some aren't, some are. It's a little confusing. I won't get into that here either. But it doesn't have that centralized body that can flip a switch and ruin access to the markets. And had these investors been on a decentralized exchange, it would have saved them hundreds of millions of dollars. And it would have prevented fraudulent market manipulation. How does it fix run of the banks? With transparency built in and automated solvency checks, you can build a bank-like smart contract that has insolvency checks built in that make it impossible to get there. Insolvent means broke as f. Any agreement or any history lesson where there was a trust assumption that was broken, smart contracts can be applied to and should be applied to, especially in a time where big money runs, owns, and controls everything. We desperately need to move to a world where some self-interested centralized entity can't flip a switch and ruin people's access to the services that they need. We can move away from a world that is brand-based to a world that is math-based. Right now, if you interact with a service that you don't like or that they break their promise, the only thing you can do is walk down the street to the next service that's going to make the same set of promises, and you have to hope and pray that they're actually going to keep it. We can move from that to a world where we can just look at the math and say, oh, okay, 1 + 1 = 2. This is what this agreement is going to do for me every single time, guaranteed. Because it's a decentralized autonomous agent, has no incentive to be evil, and everything is transparent and out in the open. If I'm a big company, and if it was better for me for 1 + 1 = 3, maybe I would go behind some closed doors and fudge some numbers and come back out and be like, hey, 1 + 1 = 3. But with smart contracts, that's impossible. Doing the right thing is infrastructural. Now, given the choice between two agreements, one where you have to trust a single centralized entity that they're going to do the right thing for you, versus a decentralized, untamperable collective, which one are you going to choose? I'm picking the one that can't screw me over every single time for every agreement I can apply it to. Now, this technology is relatively new, but we have already seen it re-landscape entire markets and continue to do so. The traditional financial world is already getting its lunch eaten by DeFi, or decentralized finance. There's already over $200 billion of people's money in these protocols to help have a more fair, more accountable, more transparent financial system. This DeFi movement is one of the main reasons I got into this space, because we desperately need to move away from where we are right now and end people's chances for wealth being sucked up by some group that's bending the rules in their favor. And smart contracts are our ticket to that better world. More and more industries are also coming over to smart contracts and blockchain because of all the innovations and because of all the advantages that it has. As we grow and as we get better, we get closer to this vision of having this concept fulfilled. Trust minimized agreements. These smart contracts are minimizing the trust that we need to give other people in order for these agreements to be executed. If trust minimized agreements is too confusing for you, just say unbreakable promises. Now, I gotta be honest with you guys. Blockchains and smart contracts and cryptocurrencies can actually do more than just trust minimized agreements. What? They have security benefits, uptime benefits, execution speed benefits, and a whole lot more. But it's a lot easier to just learn about one and learn the other ones later, right? It's kind of like sprinkles on top. So this is why we are here. This is why we're building this future. And this is why we are so excited about it. Whew. Even in just this introduction part, we've learned a ton. So let's do a quick summary of what we've learned so far. Bitcoin was the first protocol to take this blockchain technology into the limelight and take these cryptocurrencies into the mainstream. Bitcoin is a sort of digital gold, or a store of value, able to make transactions between users in a decentralized manner. Ethereum and other smart contract platforms take this blockchain technology one step further, enabling people to make smart contracts and decentralized trust minimized agreements. These smart contracts and decentralized applications can access and interact with the real world using something called decentralized Oracle networks. Chainlink is a decentralized network that allows us to build these hybrid smart contracts, which combines our on-chain logic with our off-chain decentralized data and decentralized computation, giving rise to our logic being completely decentralized and our data and external computation being completely decentralized, giving us all the features that traditional agreements and traditional contracts have. Now, these digital currencies like Ethereum and Bitcoin have value even without the smart contract part. Having a censorship-resistant, decentralized store of value is immeasurably powerful in its own right. We have some links in the GitHub repository that'll teach you how this decentralized store of value flips traditional finance on its head. And it's another one of the great reasons for building smart contracts. But again, the easiest way to boil it down is trust minimized agreements or unbreakable promises. But let's also go into some of these other features that smart contracts have over our traditional environment. The first feature, of course, is that they are decentralized and they have no centralized intermediary. The different individuals that run one of these blockchains are known as node operators. And it's the combination of all these thousands of node operators running the same software, running these algorithms, running these smart contracts that make the network decentralized. We'll dive deeper into how that works later. The next feature is transparency and flexibility. In these decentralized networks, since all these individual node operators run this software, everybody can see everything that's happening on chain, meaning there's no shady deals, there's no weird things happening. Anything that's going to be unfair, people would be able to see and just not use. Everybody has perfect information and has to play by the same rules. Now, additionally, this doesn't mean that there's no privacy. The blockchain is pseudo-anonymous, meaning that you aren't necessarily tied to an identity in real life. They also have the feature of speed and efficiency. For those of you who have ever tried to do a bank transfer or send money across seas, you know it sometimes can take 2 to 3 weeks, when in fact, all these banks are really doing is basic math. They're subtracting money from your balance and adding it to some other balance. Why does it take so long? In the blockchain, all of these transactions happen instantly. Another instance for those in the financial world today know that clearinghouses and settlement days can take a long time. In the blockchain, there's no need for any of that because they happen instantly. This obviously is much quicker, but it also makes for much more efficient interactions with each other. Security and immutability. Again, immutable means that it can't be changed. Once a smart contract is deployed, that's it. Whatever's in the code is going to be in the code forever. They cannot be altered or tampered with in any way. This means that the security is much easier. Whereas in a centralized world, somebody can hack into the server, jump into the database, and change some numbers. You can't do that in the blockchain world. And since it's decentralized, in order to hack the blockchain, you'd have to take over half of the nodes, as opposed to in the centralized world, where you only have to take over one. In the regular world, if your computer and your backup computer go down, all of your data is gone. In the blockchain world, if your computer and your backup computer go down, all your data is safe because it's being run on all these other decentralized nodes. And even if a few hundred nodes or if a few thousand nodes go down, it doesn't matter, because as long as one node has a copy of the blockchain, you're good to go. Hacking a blockchain is nearly impossible and leaps and bounds more difficult than hacking a centralized server. Not only that, but this is safer in the asset sense as well. All you need to access your credentials and your information and your assets is your private key, which is basically your password for all of this. And as we've discussed in the video, these smart contracts remove this counterparty risk, remove this centralized intermediary, remove these trust gateways that we have to do in Web 2. When we engage with users and individuals, they don't always have our best interests at heart. Smart contracts remove this counterparty risk because once one of these contracts is created, they can't go in and they can't alter it, and they can't let greed or ego or anything else get the better of them and alter the terms of the deal. And as we said, this gives rise to these trust minimized agreements, or these programmatic unbreakable promises. We move away from brand-based agreements to math-based agreements, where we can look at the cryptography, we can look right at the code and see exactly what something is going to do and how it's going to execute, versus having to rely on a human being doing the right thing. With smart contracts and decentralized hybrid smart contracts, doing the right thing is infrastructural. All these pieces boil down to us having the freedom to interact the way we want to interact without having to be afraid that interacting like that is going to screw us over. This trust minimized piece, these unbreakable promises, make interactions so much better. In the purely Web 2 world, we're constantly bombarded with messages of projects and protocols pushing us to move or act in the direction that makes them more profitable. Versus in the smart contract space, we can see everything transparently, and we can even engage and interact and be partially owners of the protocols and the interactions that we decide that we want to be a part of. So smart contracts have been around for a few years now, and what have they generated for? What industries have come about due to these smart contract platforms being around? Well, you've probably heard of some of these, and some of these we've already mentioned, but let's give you a quick refresher. DeFi. DeFi stands for decentralized finance, and it gives users the ability to engage with finance and markets without having to go through a centralized intermediary. For example, like we said with Robinhood, you no longer have to trust that Robinhood would continue to give you access to the markets. You instead would be able to see in the smart contract, yes, I have access to the markets. Or in the 2008 financial crisis, you never have to trust that these groups and institutions are giving you the correct things on the back end. You can see everything transparently right on the blockchain. You can engage with things like money markets and sophisticated financial products easy, effectively, and securely. At the time of recording, DeFi has around $200 billion in assets under management and is quickly growing. If you're really excited about DeFi, we have a ton of DeFi examples showing you how to build and interact with these protocols in coming lessons. DAOs, or decentralized autonomous organizations, are another group that we've already mentioned. DAOs are groups that are governed completely decentralized by a set of instructions or smart contracts on chain. There are some massive benefits here where engagement's much easier, the rules are black and white, and you can see everything directly on chain. Voting and governance technology is completely decentralized. And the blockchain space is one of the big ones pushing how we can evolve politics and how we can evolve governance to make it more efficient, fair, and reasonable. And you better know it, we have some examples of how to build DAOs and how to work with DAOs in coming lessons. So be sure to watch those. NFTs stand for non-fungible tokens and can really be kind of described as digital art or just a unique asset. They can do so much more, but we'll keep it high level for now. Projects like Bored Apes and CryptoPunks have revolutionized the way that people get paid for their work, show off their creativity, status, and so much more. And yes, of course, we have lessons showing you how to create and interact with NFTs as well. So many other groups and so many other industries are being created as a result of this insane technology. And maybe after finishing the journey with us here, you go out and you'll be the one to pioneer the next industry or the next billion-dollar idea. You've learned so much already. But now that we've learned a lot of this high-level information, let's finally jump in and let's make your first transaction and let's get you set up to interact with this new world. In this next section, we're going to get you a wallet and we're going to show you exactly what a transaction looks like and feels like. Let's dive in. This is the Ethereum website, ethereum.org. We are going to make a transaction on a test Ethereum blockchain. I'll explain what that means in a little bit. This is going to be our first transaction that's made on the blockchain. Now, again, this process that we're going to follow is going to work the exact same with Polygon, Avalanche, Phantom, and all these other EVM compatible blockchains. I'll explain what that means in a bit too. For now, just follow along and have fun. In order to make a transaction on any of these blockchains, the first thing that we need to do is we need to set up a wallet. So I'm going to go ahead and go to MetaMask because it's one of the most popular wallets and one of the easiest to use. We're going to go ahead and download it. I'm using the Brave browser, but it works for Chrome, Firefox, or really any other browsers. And it's just going to be a little extension in the top right hand of your browser. This way, we can really easily see at any times what we have in our wallet. This will store all of our Ethereum-based currencies. So I'm going to go ahead and install MetaMask for Brave, add to Brave, add extension, and now we can go ahead and get started with working with Brave. This is the first step you absolutely need to take when starting your journey and one of the easiest steps to take. So we're going to go ahead and get started, and we're going to create a brand new wallet. So we're going to go ahead and hit Create Wallet. If you already have a wallet, you can actually import it via I have a seed phrase. And we'll talk about this seed phrase or secret phrase in a little bit. So let's go ahead and create a new wallet. And sure, we'll agree to help out MetaMask. Now we will create our password. Make sure that this is really secure. For the purpose of this demo, my passwords are just going to be password, but please don't have that be your password. You may also get a video like this teaching you about your secret recovery phrase. This is the same thing as your mnemonic, but secret recovery phrase is a lot more clear as to what it is. And again, they give us a ton of different tips on how to actually store it and keep it safe. The main takeaway from this is never share this. Absolutely never share this. So we're going to go ahead and click Reveal Secret Words. I'm showing you guys here because this is just a demo and I don't really care. However, if you show this secret phrase to anybody else, they will have access to all the funds in your application. So everything that we're going to do in this tutorial, we're going to use fake money, we're going to use not real money, so it doesn't matter. Now, for the purposes of testing and developing, I always recommend using a completely separate MetaMask, a completely separate wallet. So for going throughout this entire course, if you already have a wallet or if you already have a MetaMask, please just set up a new one, create a new profile, create a new MetaMask, and this will be your wallet that you use for the duration of this course. However, if you're going to actually put money in here, you absolutely need to have this written down because if you lose access to this and or your private keys, which we'll talk about in a little bit, you will lose access to your wallet and you will lose access to all your funds. So they give some tips like store this phrase in a password manager like 1Password, write this phrase down on a piece of paper, put it in a secure location, memorize it. Whatever you want to do, just make sure you have this backed up somewhere. I'm just going to go ahead and hit download this for now. It's not best practice to save it to your computer. It is much better to use a password manager or write it down on a piece of paper or something. So we're going to go ahead and hit next. And it's going to ask us to verify that we actually have it written down. And we're going to go ahead and hit confirm. And great. And it gives us a couple other tips. Remember, definitely take these tips very seriously, especially if you're going to use this for real money. Like I said, for this demo, we're just going to use test money, so it's not as big of a deal, but if you put real money in, you absolutely need to back up this seed phrase or secret phrase, or we're going to refer to it as our mnemonic phrase. Awesome. Now we can see the interface of our wallet here full screened. And depending on your browser, you can actually come up and pin it to your browser so that you can just click it up in the top right and it'll drop down and you can see the same interface here. Our mnemonic phrase, that secret phrase, that secret 12 words that they gave us have given us access to a new account. The address of our account is located right here. In fact, if we click it and copy it to our clipboard and go to a tool called a block explorer called Etherscan, we can actually paste our address in here and see details about our account. Etherscan, like I said, is what's known as a block explorer, and it's a way to view different addresses, transactions, and other happenings that happen with a blockchain. If we look at this address that we just created on Etherscan for Ethereum mainnet, we can see no transactions have happened. There's really no analytics. There's no comments. There's no balance. There's no value because it's a brand new wallet. And this address that we just punched into Etherscan represents our unique address, our unique wallet, only identifiable for us. We'll talk about Etherscan a little bit more in a bit because it's a tool that we're going to use quite often. In wallets like MetaMask, you can actually even click right here and create even more accounts. So let's go ahead and create a new account. We'll call this account 2. As you can see, this one has a different address. So if we click this one, we go back to Etherscan, we paste the address in here, we hit enter, we can see another address, again, that's uniquely identifiable to us right here. It has 0 balance, no value, no transactions. Now, if we go back to our MetaMask and we click the little button, we can see we have 2 different accounts in here. It's the same if we hit the extension in the top right. Click the button, we have 2 different accounts. The 12-word secret recovery phrase allows us to create multiple accounts all with the same secret recovery phrase. So that secret recovery phrase will give us access to both account 1 and account 2 and any other accounts that we create by hitting this create account button, because it gives you access to all the accounts in your MetaMask. Now, these addresses of both of our accounts are the public unique identifiers, but they also have a private unique identifier only identifiable to us. Similar to the mnemonic, these are private identifiers we never want to share and we never want to give out. They're private. This is known as your account's private key. So the mnemonic will give you access over many of these accounts. The private key will give you access to just one of these accounts. We can see it by hitting these little 3 dots, going to account details, and export private key. You'll just have to punch in your password here, and you'll be able to see your private key. This is going to be your private key for your account. You can think of your private key as a password for your account that lets you create transactions. Now, the reason that I'm showing mine on screen is because I'm not going to put any real money in here, and this is just going to be a burner account for this tutorial. And I highly recommend, once again, you use a burner account. You use accounts that you never put any real money into. And along the way, I'll show you how to make sure that you don't do that. But normally, it's not a good idea to show or share your private keys or your secret recovery phrase. If somebody gets a hold of this private key, they will have access to my account 1. However, they won't have access to my account 2. If they get a hold of my 12-word recovery phrase or mnemonic, they'll have access to both accounts. And this is why when people say, keep your private keys safe, your keys, your Bitcoin, your keys, your Ethereum, they're talking about both your mnemonics or your secret recovery phrases and your private keys. Keep those private. Your public addresses are totally public, and anybody can view your accounts on something like Etherscan or any other Explorer, and it's totally okay for people to share their public addresses. If you lose your private key, you lose access to one of your accounts. If you lose your mnemonic, you could potentially lose access to all your accounts. Basically, what I'm trying to say is back these up and keep them in safe places. For this course, it's okay if you lose one since we're not putting any real money in them, but in the real world, be sure to do this. And great, those are some of the main security considerations here. Now, if you look up in the top right next to that account button that we've been clicking, you also see this thing saying Ethereum mainnet. This is our networks tab. And if we click it, we can see a list of all the different networks that we currently have access to. Ethereum mainnet is the main network of Ethereum. And this is where real money is spent and used for transactions. For this course, we're not going to be working with Ethereum mainnet. We're instead going to be working with something called a testnet. Since we're engineers, oftentimes we're going to want to test and see what our code is actually going to do and how to interact with it. We're going to use a combination of local networks and test networks to actually do this, to actually test our smart contracts. We're mainly going to use local networks, but we'll get to that in a little bit. To see some of the test networks that come default with MetaMask, we hit show/hide test networks. This will bring us into the settings page, and we just hit select this to show test networks in the list, and we just hit on. Now, if we scroll back up, we'll close out of the settings. We hit the networks tab again. Now we can see all of these other networks here, like Ropsten, Coven, Rinkeby, and Gorelli. These test networks are networks that resemble Ethereum or Polygon or Avalanche or Phantom or any of these other blockchains. And we can actually switch our accounts to one of these other test networks. Let's click Rinkeby, for example. we can see that on the Rinkeby test network, we also have 0 Ethereum. We have no money or nothing in here. We have a blank Rinkeby wallet. These testnets work nearly identical to how Ethereum mainnet works, except for they run with not real money. They run with fake money as a way for us to learn and interact and see how these different smart contracts actually work together. At the time of filming, Rinkeby is one of the most popular test networks, along with Kovan. So we're going to work a lot with Rinkeby in this tutorial. However, be absolutely sure to check our GitHub repository to make sure that you're always up to date with the best test network for following along with the tutorial here. Since they're test networks, people are running them out of the goodness of their hearts. And sometimes the best ones actually change. So be sure to follow along with the GitHub repository. We might also use Kovan from time to time, or maybe even Gorilla. So we're going to show you how to use a couple of these different testnets. In fact, if we go to the GitHub repo associated with this course, we can see recommended testnet is indeed currently Rinkeby. So that's what we're going to work with. Should this change, you should be able to follow along with another testnet, and we'll leave notes as to how to continue. Now, what we can do actually is we can go to Rinkeby Etherscan. So we can look up Rinkeby Etherscan, and it looks like it's the first thing that shows up. Rinkeby.etherscan.io. We can punch in this same address, copy it, paste it, and we can see some of the details of this address on the Rinkeby Etherscan. Like I said, right now it's totally blank. This network's interface later on is also how we're going to be able to work with Polygon, Avalanche, etc. We'll just have to add networks, but we'll get to that in a bit. And just to reiterate, testnets are free and for testing our smart contracts, and mainnet networks cost money and are considered live. Now, I also do want to put a caveat here that we do want to keep in mind that these testnets are being run out of the goodness of people's hearts. So we don't want to abuse them. We want to use them to learn and then move on. So try not to send a billion transactions on one of these testnets. In fact, what we're going to do right now is we're going to send a transaction on the Rinkeby testnet. And this will show us exactly what it would look like on a main network. In order for us to simulate one of these transactions, we're going to go to what's called a faucet. And if you go to the GitHub repository associated with this course, right underneath the recommended testnet is going to be a testnet faucets, which is going to show us where the most up-to-date faucet location is for us getting testnet Ethereum. So here we are at faucets.chain.link, which again is the recommended faucet. And what we can do is we can actually put our wallet address in and get some testnet link or testnet Ethereum. Now, what we are going to have to do is we are going to have to connect our wallet to the Rinkeby network. So we're going to come down, we're going to switch from Kovan to Ethereum Rinkeby, and then we're going to make sure our MetaMask is on the Rinkeby test network here. Once both of those are set up, we're going to go ahead and hit Connect Wallet, and we're going to choose MetaMask. Once we do that, our MetaMask is actually going to pop up and say, would you like to connect to this website? Connecting to a website is how we give these websites an interface to interact with our wallets and interact with our MetaMasks. Don't worry, we're not sending any transactions like this. We'll get to that in a bit. So we can pick an account we want to connect. Let's choose our account 1. We'll hit next, and then we'll go ahead and connect. Now that we're connected, we can actually see our account connected up here, and that little warning is now gone. And our wallet address is automatically placed into here. We're going to make our first test transaction. And for now, we don't need test link, so we're going to leave that off. But later on, we're going to come back and get that test link. For now, we're just going to need 0.1 test Ethereum. So let's go ahead and complete the security by choosing the traffic lights. And we're going to hit send request. What this is going to do is we're asking this faucet to send us 0.1 test Ethereum. Testnet faucets are ways for us to get money into our wallets on a testnet. And this is why this testnet Ethereum isn't worth any actual money, since we can get it for free. These don't exist on mainnets. You can't get real Ethereum or real money for free on a main network. So we're on Rinkeby, we're getting fake Rinkeby Ethereum, and we're going to go ahead and hit send request. Once we hit send request, this transaction hash is going to pop up here. And it says transactions have been initiated, waiting for confirmation. This means that some other wallet is actually going to send us 0.1 test ETH, And this is the transaction that it's doing to do that. Now we just have to wait for our transaction to finish verifying and finish going through. So now, if this doesn't work right away, I would recommend wait a minute and then just try it again. But what we can do is we can click this transaction hash. If that transaction doesn't show up, we can also just close this and we can copy our address here. And actually, we already see 0.1 ETH in our wallets here, but we can go back over to Rinkeby Etherscan, paste our address in, and we can see that we now have 0.1 Ether as a balance. We can also see that we have a transaction with all this information going into our wallet. That's what this green in is for. If you click that transaction link, you'd get something like this. But if you didn't, don't worry, because on the Etherscan, if you click the transaction hash in the transaction list, you can also see all the details like that. So now in our MetaMask, we have 0.1 ETH. Again, this is fake Ethereum, and we have a transaction associated with our wallet now, which is awesome. Again, though, if we switch networks back to Ethereum mainnet, you can see that we have nothing on Ethereum mainnet. Or if we go to Ropsten, we also have nothing. We only have this 0.1 ETH on the Rinkeby test network. If you want to practice working with another testnet, and the faucet that we're using has multiple testnets, let's go ahead and try it. Doing this section right now is completely optional. You can watch or you can follow along. But for example, I can see in my wallet that we already have Coven supported. So maybe I'll switch to Coven. Maybe we'll switch to Coven in the drop down here. We'll remove test TED link because we only need test ETH. We'll hit I am not a robot and we'll send request, and the same things will pop up. This time, this is going to be for the Coven testnet. And once our transaction finishes going through, now, same thing on Coven here, like what we did with Rinkeby. Once our transaction finishes going through, we'll see 0.1 test ETH on the Coven network. If you want to go ahead and try working with another one of the testnets, like maybe, for example, Coven, I recommend you go ahead and giving it a try, but it's completely optional. And I would always refer back to the GitHub repo to make sure you're working with the most up-to-date faucet and testnet. And if we look back at Etherscan, we can actually see more details on what actually just took place. What actually just happened? How did our MetaMask get a balance of 0.1 ETH all of a sudden? Well, if we look down in the transaction section, we can see that there's a transaction here. Some address sent us 0.1 Ether. And if we click the transaction hash, we can see more details about what actually went down with this transaction. Now, understanding what's going on in this transaction is essential to learning and being a smart contract developer or just engaging with the ecosystem. So let's learn. The first bit at the top is this transaction hash. This is a unique identifier for this blockchain or this testnet that identifies this exact transaction. This transaction hash identifies sending 0.1 ETH to our address. We can see that the status of this transaction was successful. It didn't break in any case. We can see the block number that this transaction was included in, and we'll get to blocks in a little bit. We can see the timestamp, which of course is when this transaction occurred. We can see which account it was from, which if we go ahead and open in a new tab, we can see that this is the account that this transaction came from. And it's got 3 million Ether. Of course, this is fake Rinkeby Ether, so it doesn't really matter. We can also see who it was to, which again is just us. This is our wallet address, 0x1066, blah, 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 0x1066, blah, 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 right? The value of this transaction, of course, is 0.1 Ether. Now, what's all this that we see past the value? So obviously the value is 0.1 because that's how much we sent, but we see this transaction fee and this gas price. We hover over the tooltip, we can see, if you zoom in on your Etherscan, you see amount paid to the miner for processing the transaction, and we see a gas price, which is cost per unit of gas specified for the transaction in Ether and Gwei. The higher the gas price, the higher the chance of getting included in the block. Now, if we scroll down even more and we click see more, we can also see a ton of other information here. For now, we're just going to click to see less and just focus on these two. I'll explain all of these in a later session. Let's talk about just the concept of transaction fees and gas for a second. Remember how I said the blockchain is run by all these different nodes? Well, all those different nodes are running this blockchain because they actually get paid for all the transactions that happen on these blockchains. Whenever you make a transaction, there's a node or a miner or a validator. Somebody running the blockchain software is going to get paid a tiny bit of Ethereum or Polygon or whatever blockchain that you're running on. They're going to get paid a tiny bit of that native blockchain currency. This payment is obviously to incentivize people to continue to run nodes. And they calculate how much you pay and how much the node operators get paid based off of how much gas you use. So there's this concept of gas. Gas is a unit of computational measure. The more computation a transaction uses, the more gas you'd have to pay for. For example, we do hit click more just really quickly. We can see this section saying gas limit and gas usage by transaction. There was a limit of 60,000 units of gas on this transaction, and 21,000 were actually used. So this transaction used 21 units of gas. Now, for very simple things like sending Ether, the units of gas are usually pretty cheap. But maybe for more complex things like minting an NFT, depositing to some DeFi contract, etc., maybe those will cost more gas because they'll be more computationally expensive. If this is a little confusing right now, don't worry too much about it. But just know that we use 21,000 gas here. And if we pull out the calculator, 21,000 gas times this gas price right here, times the gas price, we get the exact same as we see for the transaction fee. So gas price times how much gas you used is the transaction fee. So whoever sent us this 0.1 Ether also paid 0.0000525, etc. Rinkeby Ether to make this transaction. Now, each blockchain has a different way of actually calculating how this gas stuff works. So that's basically going to be the high level of it. So we're going to focus just here for now. There's a total transaction fee, and then there's obviously the gas price. After we cover how blockchain works, I'll explain what this burnt stuff is, these gas fees, and all these other stuff. For now, just know that anytime you make a transaction on chain, you have to pay a little bit of what I call transaction gas. So for example, if we go to our MetaMask, we have two accounts right here. We have account 1 with 0.1 Rinkeby ETH and account 2 with 0 Rinkeby ETH. If I were to send 0.05 Rinkeby ETH from this account to my other account, how much Rinkeby ETH do you think I'd have left? Well, let's go ahead and try it. This will be the first transaction that you're actually creating that you are going to spend the gas for. So if we go ahead and hit send, we'll hit transfer between my accounts. Account 2, we'll do 0.05. Next, we can see some information here about what's actually going on. MetaMask has some new advanced gas fee UI and settings. We're also going to turn this on. So go ahead and click that, enable enhanced gas UI, turn that on, and then go back. And again, this is going to be the experimental tab, but it could also just be in the general settings tab, depending on when you actually run this. We can see a little notification here. Again, this depends on what version of MetaMask you're using. And we get this little drop down that says, here are some of the different type of gas fees that you can actually pay. The reason that gas fees might change, as you can see here, is that depending on how busy the blockchain is, you have to pay more gas. If a lot of people are sending transactions, that means there's not going to be enough space for everyone's transaction to get through. That's a bit of an oversimplification of what's happening, but don't worry too much about it for now. Now, if we want to send this 0.05 Ether to our second account, we can see this gas estimated section, which is saying it's estimating we're going to pay 0.00004792 gas, in addition to sending the 0.5 ETH. So at the bottom, we have amount plus gas fee, and this is going to be the total amount that we're going to be spending on this transaction. 0.05 is what we're sending, and then we also have this gas piece. So we go ahead and confirm. We now see we have a transaction pending in our Rinkeby Etherscan, and if we click on it, we can even hit View on Block Explorer, and a Rinkeby transaction hash will pop up. And depending on when you click it, it might say indexing. This means that Etherscan has received your transaction and is trying to place it. If you don't see anything here, it means that maybe the transaction hasn't gone through yet. Maybe you need to wait a little bit more, or maybe you need to go back to the GitHub repo and pick the recommended testnet and faucet. So you might have to wait a minute or so for this to actually finish indexing. After a minute or so, we can see that this transaction has indeed passed, and we can see a lot of the same information that we saw on our last one. this time with 0.05 Ether. And now if we look in our MetaMask, we can see account 1 has 0.05. It's rounding up a little bit. If we click on the big button, we can see it actually has 0.049953, etc. And our other account, account 2, does have exactly 0.05. This is because we spent a little bit of Ethereum on gas to send this transaction. And now, with just this little bit of information, you know how to actually interact with applications that use the blockchain, how to send transactions, and a lot of the non-technical details.
Now, here's something that's incredibly exciting. With just this little bit of information, you now know how to interact with blockchains and interact with the Ethereum protocol. So if you don't want to learn how to code anything, you can go and you can start interacting with Ethereum and interacting with protocols with just this much information. However, I know most of you guys are here to learn how to code. So let's look under the hood of Ethereum and what is actually going on with these transactions and with these gas and with these blockchains and what's really going on. Let's learn all the fundamentals of a blockchain. Now, if you want to just go ahead and jump into the coding, go ahead and grab a timestamp from the description. However, learning exactly how the blockchain works is going to make you an incredibly powerful developer. So let's take a look at that first. So we're going to be going through this blockchain demo on this site right here. Now, the creator of the site has a fantastic video and a fantastic walkthrough. Blockchain 101, it is right on their site. So if you're looking for another explanation, definitely check out his video. It is absolutely fantastic. But the first thing that we really need to do in order to understand blockchain, in order to understand really anything and everything that's going on here, we first really need to understand this SHA-256 hash or hashing just kind of in general. Let's first understand what a hash is. A hash is a unique fixed length string meant to identify any piece of data. They are created by putting some piece of data into a hash function. In this example, the hashing algorithm used is SHA-256. Now, Ethereum actually uses this right here for its hashing algorithm, which isn't quite SHA-256, but is in kind of this SHA family. But it's really just another way to hash things, and the specific hash algorithm doesn't matter so much. So this example uses SHA-256, but you can imagine it's the same as the Ethereum hash. They're just going to result in a different hash. So what's going to happen in this application here is whatever data or whatever information we put into this data section here, as you can see below, this hash changes. So what's happening is this data is running through the SHA-256 hash algorithm, and it's outputting this unique hash. So this hash is a unique fixed length string that's going to identify like a blank data piece here, right? So if I put in, my name, like, Patrick Collins, this is the hash that's going to represent Patrick Collins, right? And you can see, even when I put, tons and tons of data in here, the length of the string doesn't change, right? So it's always going to be the same amount. We can put almost any amount of data in here. There is an upper limit on the max size of the data, but for all intents and purposes, we can pretty much put any length in here. And you'll see too that, every time I type in Patrick Collins, this hash is always going to be this 7E5B, right? I'm going to delete it. I'm going to do Patrick Collins again, 7E5B. It's always this unique hash is always going to be unique, right? It's always going to be this fixed length string here. So now we can take this idea, right, of putting this data in here, and we can move on to this concept of a block. So with this block concept, we're going to take the exact same thing with this hash, this data section, right? But instead of having everything just being in this singular data area right here, we're going to split this data up into block, nonce, and data. So what we're going to do is we're actually going to hash all three of these to get this hash, right? We're going to put all three of these. We're going to say all three of these are combined together. We're going to put all three of them into this hashing algorithm to figure it out. So if I type a bunch of stuff here, we can see that block 1 with nonce, this nonce and this data, we're going to get this hash. And as you can see, actually, the screen turns red. This block turned red. Now, what happens when I hit this mine button? When I hit this mine button, it's actually going to take some time. It's going to think for a little bit. And we can see that the nonce here actually changed, right? The nonce is different from what it was before. And this hash now starts with 4 zeros. Okay, and then the back turned green. When we're talking about mining, we're talking about miners solving some type of very difficult problem that takes a lot of time to do. Now, in this example here, the problem that the miners had to solve was they had to find a nonce or a value in this nonce section that when hashed with at block number 1 with this data, it would start with 4 zeros. So the problem here the miners had to solve was to start with 4 zeros. And the only way for them to really do that is kind of this brute force, trying stuff. So they tried 1, okay, 1 didn't work. Okay, 2, nope, 2 didn't work. 3, no, 4, 5, 6, okay, 5, well that started with 1 0, but that's not 4. And they have to keep trying all these numbers until they get to this one where, let's hit mine again, where it has 4 zeros at the top, at the start. Now, this specific problem changes blockchain to blockchain, right? Ethereum has a different problem for miners to solve. Bitcoin has different problems for miners to solve, but this concept is going to be the same. So they have to take one block is going to be this concept is going to be all this data. It's going to be the block number, and it's going to be this nonce, right? And so this nonce is the solution. Is going to be the number that they use to get like the solution to the problem, right? So if I go to 1 here, and I do this again, I'm going to hit mine, and the nonce has changed, right? It went from 1 to 33,128 because this is the nonce that allowed this hash to start with 4 zeros. And so that's what's happening when blockchain miners are mining. They're going through this process, this very computationally intensive process of trying to find a nonce that fulfills whatever the problem is. So that's really it, actually. So that's a block, and that's really what's happening when miners are mining. They're just looking, there's trial and error, brute force, trying to find this nonce. So now that we know what a block is, let's go to the next step and figure out, okay, well, what's a blockchain? So here we have an example of what a blockchain is going to look like, right? We have a combination, we have back here in the block section, we have what one block looks like. Now here we have multiple different blocks, right? Each one of these represents a different block, but we have an additional column here, or we have additional variable here. So like before, we have block, nonce, and data, right? We have block, nonce, data, but we also have this thing called previous, right? And so this is actually going to be pointing to the previous hash of the last block. So for example, if we go to the last block in this blockchain, it says previous is 00AE8, and if we look at the hash of block number 4, it's 0000AE8. And then we look at its previous, it's 4 zeros B9, we have 4 zeros B9, and so on, all the way back to our first block, which has previous of just all zeros, right? And so the block with the previous of all zeros is going to be known as the Genesis block. So you've probably heard that before, the Genesis block. It's the first block in the blockchain where the previous hash points to a hash that doesn't actually exist. Now, as you can imagine, kind of the same as how this block worked, how the block, nonce, and data all go through the hashing algorithm. In the blockchain, the block, nonce, data, and previous hash all go through this hashing algorithm to figure out, what the hash is, okay? So if we go to over here, for example, if I type in, Patrick, obviously this is now no longer valid, right? Because this nonce combined with the block, the data, and the previous hash aren't going to solve, our problem of having 4 zeros at the start, right? So I'm going to go ahead and fix that, and that's kind of an easy way to see it being broken. But let's take a look. If I break this block right here, what happens if I break the data in here? If I do like Patrick in here, you can see that both of these are now red. Both of these are now invalid, right? Because the block hashed with the nonce, hashed with the new data, which is my name Patrick, hashed with the previous block, is now a brand new hash, right? And this block is still pointing to this previous hash right here, right? Is pointing to this previous block, and now it is wrong and it is messed up, and now its nonce with this previous hash is also wrong, right? And this is where, when we talk about blockchains being immutable, this is exactly how it's immutable, right? Because if I go back and I change anything, if I just typed A right here, the entire blockchain is now invalidated because none of these are going to have nonces that solve this equation anymore. So this is why blockchains are immutable, is because anytime you change one thing, you ruin the rest of the blockchain, okay? So however, though, if an A was here originally, we can go ahead and mine these. We can mine all these, but as you can see, this is going to start getting very computationally expensive because I have to go redo basically the entire blockchain And the farther and farther down the line you get, the harder and harder it becomes to rehash and redo all these different blockchains here. Now, this makes a lot of sense, right? So we have this blockchain. It's really hard to change something in the past, but if we do, we can just go ahead and remine it. Now, if I'm the one who controls the blockchain, right? If I'm the one who controls this, and I want to change something in the past, well, okay, great. All I got to do is change this data here, and then mine each one of these. Obviously, it's going to be very computationally expensive, but it's something that I can do, right? If I'm the one who owns the blockchain. Now, here's where the decentralized nature or the distributed nature really makes it incredibly powerful. So we're going to go to the distributed tab here, which I also refer to as the decentralized tab here. And it's going to show us what a blockchain looks like in a decentralized manner. So we have this exact same initial setup here. We have distributed blockchain. We have our first blockchain, which is kind of exactly as the one from here. But we also have more than one. So we have peer A, peer B, and peer C. And when people are talking about peer-to-peer, peer-to-peer transactions, they're really talking, this is kind of that concept that they're talking about, right? So we have a number of different peers who are running this blockchain technology. They're all weighted equally, right? Each one of these peers or each one of these nodes, each one of these entities running a blockchain has the exact same power as anybody else, right? So the way that we can tell very easily which blockchain is correct or which ones are correct are by looking at this end hash here, right? Or by looking at where we are in the blockchain. Because again, remember, this hash that this in this last block here is going to encompass all of the blocks from before, right? Because this last hash is going to have the previous hash here, which includes the previous hash here, which this hash includes the previous hash here, and so this last hash encompasses everything in here, right? And we can look at the hash of peer C, which is 4 zeros and then E4B. We can look at the latest hash of peer B, which is 4 zeros E4B, and then peer A, which is 4 zeros E4B. So all of these peers, all of these nodes, all of these decentralized, these independent, all these independent users running this blockchain software, they're all matched up. It's very easy for their nodes to look at each other and say, hey, great, we are all matched up. Now, let's say that A decides that something happened on the blockchain that they didn't like and they wanted to go back and change something, right? So let's say they change here. Obviously the rest of their blockchain is invalidated and they have to spend a lot of computational power to catch up to speed. So let's go ahead and humor it. Let's say that they did. They ended up catching up. They ended up mining everything. And now they have a valid blockchain, right? It solves the equation. Awesome. However, in block number 3, there's something new, right? This is here and it shouldn't have been here. This is something that peer A put in by themselves. All that happens now is we look at all the blockchains that are running the software and we're looking at all the hashes at block number 5. So peer A has this new hash now, 0009BC, but peer B has a different hash, 000E4B, right? So who's right? Is it peer A with their new stuff or is it peer B? Well, that's where the decentralizer comes in, because then we can look at peer C, and peer C also has E4B. So peer B and peer C both say, hey, peer A, you're wrong, get out, right? And peer A will stop being able to participate in the mining rewards because they have essentially forked the blockchain and started their own little blockchain, right, with their own history, because they're the only ones with this piece of data in block 3, whereas peer B and peer C have nothing in there. So that really shows why in these blockchain worlds, in this decentralized world, there really is no centralized entity. Peer A, might have been maliciously motivated to change, this block number 3. However, democracy rules, right? The majority rules in the blockchain. Peer B and peer C both say, hey, that's cute and all, peer A, but you're wrong, right? That's not right. Now, it might be a little abstract to just look at data and, us typing kind of random stuff in here and think, okay, yeah, that's data, right? That makes sense. Just kind of random strings in here doesn't really do anything for us. So if we actually go over to the token section here, this is where everything really starts to make a lot of sense. So we have the exact same setup here with peer A, peer B, peer C, except the difference is instead of having kind of this data section, we have this TX, this transaction section, right? And this represents all the transactions that are happening in this block, right? So we're sending $25 from Darcy to Bingley, $4.27 here, 1922, right? And it's the exact same thing. So all these transactions are going to get hashed in the exact same way that the data is going to get hashed. And this is why it's so powerful, because again, if I want to be malicious, right? If I want to say, hey, I really wanted to give Jane a lot more money from Elizabeth, so I'm peer A, and I go back and I change it to 100. Well, now, not only does my whole blockchain get invalidated because that was so long ago, but I'm not going to match any of these other chains, right? And so my blockchain is going to be excluded from the overall blockchain. So, and let's go ahead and fix this. And it's the same thing. If down here, if I become malicious and I want to send, I want Miss Audrey to have less money, maybe I want to send $1, and I go ahead and mine it. The same thing here. This hash now, this 2A1 is not going to match peer B's hash of BBA, and it's not going to match peer C's hash of BBA as well. So the two of them are going to say, hey, your blockchain is invalid. It's not matching the majority. You're out, right? So that's really how these blockchains work at a low level. And it all goes back to this understanding this hash idea and using it in this very sophisticated manner to kind of cryptographically prove where stuff lies. Now, the way the blockchain works is that instead of random stuff put in this data section, it's actually going to be Solidity code in here, defining ways to interact with different blocks and different protocols that are on chain, or, as we've said before, different smart contracts. Now, the next question that you might be asking is, okay, well, how do I know? How can I be sure that I'm the one? Let's say I'm Darcy, right? How can I be sure that Darcy was the one to actually send this money here? How do we know that Darcy sent $25 to Bingley? Well, this is where we get into private keys and public keys, and that's what we're going to go into now. Let's just do a quick recap of what we've learned in this section so far, right? We've learned that Ethereum actually runs on this Kitchak 256, but we used SHA 256 for this demo. It doesn't really matter. We're just talking about hashing algorithms. So again, a hash is a unique fixed length string meant to identify any piece of data. A hash algorithm or a hash function is a function or algorithm that computes any type of data into a unique hash. Mining is going to be the process of finding the solution to the blockchain problem. In our example, the problem was finding a hash that starts with 4 zeros. Nodes get paid for mining different blocks, and the problem is going to be different blockchain to blockchain. A block in a blockchain is basically a combination of a block, nonce, transaction, and a previous hash to create this unique hash for this block. And again, depending on the blockchain implementation, this might have a couple other fields or might have different fields, but this is essentially what's going on. Blockchains are decentralized and distributed because many independent users are going to run this blockchain software, and it will check and they will compare against each other to see which blockchains are acting honestly and which ones are acting maliciously. In the blockchain world, majority rules. The nonce here is the answer used or the number used to get this hash. Now, nonce is kind of an overloaded term. It's actually used for a number of different reasons. In this case, we're using it to solve this problem of getting 4 or 5 zeros at the stop of the hash. However, in Ethereum, it'll also be often used as the number of transactions from a given address. So now we're going to talk a little bit about signing these transactions and private keys and some other cryptography pieces, right? Because in this blockchain demo here, we can see we have all these fantastic transactions, right? All these things went through. But how do we know that it was Darcy who was the one to send $25 to Bingley, right? How do we know that actually happened? And this is where all those pieces that we just learned about in our testnet, in our MetaMask account, are really going to start to come to life here a little bit here. So here we have an example of public and private keys. Okay, at the top we have this private key, right? That was randomly generated. A private key is as it kind of states, is a key that you really want to keep secret because you're going to be using this as kind of your secret password for all your transactions, right? I can really pick any private key, anything that I want, and with it, this algorithm, they're going to use an algorithm. For Ethereum and Bitcoin, they both use this elliptic curve digital signature algorithm. It's a variant of just a digital signature algorithm, and it's going to create this public key, right? I'm really not going to go at all into kind of this digital signature algorithm, but just know it does use some of some of the hash knowledge that we just learned, combined with some other pieces to kind of get this public key here. So I'm not going to go too deep into it, but we have this private key that we create, and we get this public key. Now, this public key we want everybody to have access to, right? This is, yeah, whole world can see this. This private key, we really want it to be private. We don't want people to see this. We're going to use this private key as like a password to quote unquote digitally sign transactions. And then people can verify them with this public key. So let's see what this actually looks like. Let's pick a random key, a more secure key, right? Because the longer it is, the more secure it's going to be. And if we go to signatures now, right? Let's say we have this this message that we want, right? We'd say "Hi world," right? We want this to be the message. What's going to happen is this private key that we've created, we can use to sign this data, right? Remember how in the blockchain demo, you know, we were hashing stuff, right? We're using this SHA-256 hash to get this hash. Well, we're doing something similar, but instead of hashing, we're using this digital signature algorithm to create this message signature. Now, what's really powerful about how this algorithm works is that you can create this message signature with your private key, but somebody else can't derive your private key from the message signature. And that's what makes this really, really powerful. However, if we go to verify using this public key, right? And so this is that 0403. This is that same public key. Using this public key, anybody can verify. Oh, let's go ahead and sign it again. Anybody can verify that this signature is yours, right? So you have a private key just for you, so you can sign things, and a public key so that anybody can verify something, right? So anybody can verify this, and let's say somebody tries to fake a transaction from you. They say, "Hey, you know, this is their transaction." All they have to do is verify that this signature against your public key, and very easily this whole thing turns red because it isn't verified, right? The algorithm says, "Hey, that's wrong." So we can go ahead and take that into transactions in this exact same way. So if I want to send money, you know, if I want to send $400 from, you know, my address to another address, using my private key, I can sign that transaction, and anybody else in the world can then verify this transaction, right? And this is why when people say hide your keys, you know, protect your keys, this is what we're talking about. In our accounts here, right? If we go to settings, and again, the only reason that I'm showing you guys my mnemonic and my private key is because this is a dumpster account. I'm going to throw this away at the end of this video, or I'm just not going to put any real money in it. But when we look at our MetaMask here, we have this mnemonic phrase which allows us to easily get these different private keys, right? So mnemonic phrase combined with, you know, whatever account number will get us a private key. So mnemonic phrase combined with 1, we're going to get this private key. And this is when we look at account details, export private key, password confirm. This is going to be the private key that we're going to use to sign our transactions, right? This, if anybody else gets access to this private key, they then can sign transactions for us, and they can send transactions for us. And that's why we want to keep these private. So it works the exact same way, right? And so this is why it's so important to hide your private keys and hide your mnemonics. Now, your Ethereum address is actually a piece of your public key. Now, to get our address in Ethereum, all we have to do is take this public key that we've created with our private key, hash it using that same Ethereum hashing algorithm, and then take the last 20 bytes. And that's how we'll actually derive to our address here. Now, knowing the exact methodology of how to get the address doesn't really matter because it could change blockchain to blockchain and could even change in ETH2. But just know that that is essentially how kind of these addresses are derived, right? There's some derivative of the public key, right? Because the public key is public, and you know, using the public key in kind of any public way is totally fine, but not the private key. So that is how we sign our transactions. Note though, this isn't how we send the transaction. So this is just going to sign it, create a transaction for us to send. We'll learn later on how to send these transactions. Whew, so that was a lot of information there too. Let's do a quick recap. Your public key is derived by using a digital signature algorithm on your private key, right? And you want to keep your private key private at all times because you're going to use your private key to sign transactions. Signing transactions with your private key, you are the only one who can actually do this because you can't get the private key from a message signature. However, using your public key, anybody can very easily verify that a signature that's signed by you is in fact signed by you. In our MetaMask, our private keys are located in this account details section. You just hit show private keys and type in your password, and you'll get your private key here. A quick note here is oftentimes when using your private key somewhere, they want it in hexadecimal form. So if we're going to use our private key for something like Brownie, which we'll go into later, we need to actually append a 0x to the front, but we'll get into that later. And the address of your account is derived from this. So if you think about it, your private key creates your public key, which then can create your address. And there's a little barrier here, or a big barrier here, because your private key you want to keep private, and your public key and your address can all be public information.
Now that we know a little bit more about what's going on underneath the hood of these blockchains, let's go back at our transactions and look at this gas thing again, and we'll look to see what's actually happening here. Gas in particular can be a little bit tricky to wrap your head around. So if you don't get it right away, don't worry. As we go through examples, it'll start to make more sense. So before I was saying, let's just look at this transaction fee bit, which is the cost associated with running this transaction. If I scroll over this on Etherscan, I can see this thing that says block base fee per gas plus max priority fee per gas times the gas used, which might be a little bit confusing here. Let's actually break down what's going on Ethereum with EIP 1559 in place. And again, this is going to be specific to Ethereum as every blockchain might do it a little bit differently. But if we click to see more, we can see a number of useful values here. We can see gas limit is 21,000 and usage is 21,000. So this transaction used 21,000 gas, and we sent 21,000 gas along with it. Sometimes when sending a transaction, depending on when it's sent and depending on what the specific instructions are, it might actually use way more gas than what you want it to use. So with your transactions, you can actually set a limit. Hey, I don't want to use more than X amount of gas. I don't want to do more than X computational units. And in fact, if we go to our MetaMask and we click send to transfer between accounts again, and we pick, 0.01 ETH or something, next, we can actually hit this little button here, go to advanced, and we can actually edit some specifics of this transaction. One of them is going to be the gas limit. We can change this gas limit to maybe 2,200, 2,300, or more, or even less. Since sending Ethereum takes exactly 21,000 gas, MetaMask just defaults to setting it to that. But we also see these other interesting things. We see a priority fee and a max base fee. Let's reject this transaction and let's look back at Etherscan to talk about these. So currently in Ethereum, according to EIP 1559, every transaction on Ethereum comes with something called the base fee. This is the minimum gas price you need to set to include your transaction. And you'll notice that these are priced in something called GWEI. So what is a GWEI? If we come to the site ethconverter.com, and again, there's a link to this in the GitHub repository, we scroll down, we can see WEI, GWEI, and Ether. If I put 1 Ether in here, I can see how much 1 Ether is in terms of GWEI and in terms of WEI. 1 Ether is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So that's 1 billion GWEI is going to be 1 Ether. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then 18 zeros is a WEI. These are just easier ways of referring to really, really small amounts of Ethereum. So if we look at our gas fees, we see that the base fee is 0.0000004 GWEI. And this obviously would be an even smaller number if this was in units of WEI. So if we take this number and we put it into our calculator, we can see that this is equal to 40 WEI or 0.00000, a whole bunch of zeros for Ether. The max fee here refers to the maximum gas fee that we're willing to pay for this transaction. And you can actually see that our max fee is a little bit higher than what we actually ended up paying. Our max fee was 2.2132 something something, and the gas price we actually paid was up here. Now your transaction might, of course, be a little bit different. Then additionally, we have a max priority fee. This is going to be the max gas fee that we're willing to pay, plus the max tip that we're willing to give to miners. Now, currently in Ethereum, this base fee ends up getting burnt. And we can see on Etherscan exactly how much is getting burnt here. And if we pull up our calculator again, we can grab this gas fee, multiply it by the amount of gas we used, and we can see that this is indeed how much Ethereum we actually ended up burning. We go back to an Ethereum converter, paste it in, we can see that these two numbers are indeed equal. This means whenever you send a transaction, a little bit of Ethereum is removed from circulation forever, or it's considered burnt. So currently in Ethereum, part of your transaction fee actually gets burnt, and then the other part goes directly to miners. So to figure out exactly how much went to miners, we could do this number minus the burnt amount. And this is how much Ethereum was paid to an Ethereum miner for this transaction. You'll see down here, transaction type 2, EIP 1559. This is the EIP 1559 version of these transactions. Like I said, every blockchain is going to have a different fee burning and fee and gas process, and they're all going to be a little bit different. But the sum of it is blockchains have limited block space for transactions. The gas price that costs for your transaction to be included in one of these blocks changes based off how much demand there is. The base gas fee for Ethereum will go up and down depending on how many people are sending transactions and how many people want to be included in a block. If a ton of people want to be included in a block, that means a ton of gas is obviously going to get burnt. We've left a link to a video in the GitHub repository with this section from this YouTuber who does an amazing job breaking down this EIP 1559 and more about how this gas model actually works. I highly recommend you pause this video and watch that video to understand more. The base fee gets programmatically, algorithmically adjusted to try to target for all the blocks to be 50% full. If they're more than 50% full, this base fee automatically goes up. If they're less than 50% full, this base fee goes down. Now, this is a lot of the basics of how this transaction works, and it can be a little confusing. So let's do a quick refresher of everything in here. There's a unique transaction hash that uniquely identifies this transaction on this blockchain. We can see the status. We can see the block number that it's confirmed on. One other thing we want to look at, if we scroll up, we see block number and block confirmations. This is how many blocks have been mined since this block was included. Like we saw with our blockchain demo, the longer the blockchain gets, the harder it is to tamper with and the more secure it is. Typically, you'll see some processes say they'll only do something after 20 block confirmations, 30 block confirmations, or etc. The reason that they wait for these block confirmations is because they want to make sure that that transaction is actually included. And we can actually see the block that our transaction was included in and all the other transactions with it, different details about how much gas was used, the gas limit, etc. Timestamp is when the transaction happened. We can see from and to, we can see the value, and then we can see the transaction fee, which we see right here is block base fee per gas plus the max priority fee per gas times the gas used. And we see all the details of the gas down here. Gas price is the cost of 1 unit of gas. Gas limit is the max amount of units of gas that we're willing to pay in this transaction. The usage is how many actually got used. The base fee is going to be the base network fee per gas, so 40 Wei per 1 gas used. The max gas is the max gas price we're willing to pay, and max priority is going to be the max gas price plus the tip that we give to miners. And then we can see how much is burnt, and then we see transaction savings, which is the difference between how much was actually used or paid for and then returned. So for example, in this transaction, the gas price we ended up picking was a little less than our max gas price here. So the gas price we ended up using was a little less than our max priority fee here. So we had some savings compared to that. We can also see that this was an EIP 1559 transaction. We can see our nonce here, which was nonce 0 because the transaction that I'm showing is our first nonce. And then of course we can see the input data. For transactions that are just sending Ethereum, the input data is going to be blank. But you'll see that when we get to smart contracts, the input data is not going to be blank, and it's going to be one of the most important features of these transactions. You'll also notice that there's a state tab. This is an advanced tab, and it shows the different states that are changed based off of this transaction. We're going to ignore this one for now. Now that we know how the blockchain itself works under the hood, let's talk about some blockchain fundamentals. And we actually covered all these topics in a previous FreeCodeCamp video. So let's go to that. If the first time you listen to this, some of these concepts seem a little bit hard to grasp, don't worry about it. As we continue and as we move on with this course, they'll start to make more sense when you see them used in real examples. I definitely would recommend going back and rewatching and re-listening to the parts that you don't quite get and asking questions in the discussions tab of the GitHub repository.
Awesome. So now that we know all the cryptography pieces and all the little nitty gritties of how the blockchain actually works and how our signatures work and how everything sticks together, let's talk a little bit about how this works in actuality and what's really going on. Now, for a lot of this, each different blockchain has slightly different algorithms and slightly different metrics and criteria for doing a lot of this stuff. So when we're talking about these specific implementations, keep in mind the exact algorithm might be a little bit different, but the concepts are all still going to be exactly the same. Hashing and a hash function is going to be the same no matter where you look. A decentralized blockchain is going to be the same no matter where you look. How it's actually implemented is going to be a little bit different. Now, traditionally, when you run an application, be it a website or something that connects to some server, you are interacting with a centralized entity. And unlike how we saw with the blockchain with multiple different peers, it's going to be run by a single centralized group. Now, it still could be run on many different servers, but all those servers are still going to be controlled by the same centralized group. Blockchains, as we saw, run on a network of different independent nodes. When we saw peer A, peer B, peer C, those were different examples of different independent users running the blockchain technology on their own node. Now, when I use the term node, I'm usually referring to a single instance of a decentralized system. So when I say a single node, when I'm talking about a blockchain, I'm talking about one of those peer A's, peer B's, peer C's running that blockchain software. I'm talking about one server running this technology. And again, it's this network, it's this combination of these nodes interacting with each other that creates this entire blockchain. What makes these so potent too is that anybody can join the network, and that's why there's decentralized. The barrier to entry is a little bit of hardware requirements, you getting the correct materials to run the software, and then you running the software. Anybody can join these networks and participate, and that's what makes it truly decentralized. In fact, you can go to GitHub right now and run your own Ethereum node in a few seconds. Now, in the traditional world, applications are run by centralized entities. And if that entity goes down, or is maliciously bribed, or decides that they want to shut off, they just can't, because they're the ones that control everything. Blockchains, by contrast, don't have this problem. If one node or one entity that runs several nodes goes down, since there are so many other independent nodes running that it doesn't matter. The blockchain and the system will persist so long as there is at least one node always running. And luckily for us, most of the most popular chains like Bitcoin and Ethereum have thousands and thousands of nodes. And as we showed in our demo, if one node acts maliciously, all the other nodes will ignore that node and kick that out or even punish it in some systems, because they can easily check everybody else's node and see, okay, this one is out of sync with the majority. And yes, majority rules when it comes to the blockchain. Each blockchain keeps a full list of every transaction and interaction that's happened on that blockchain. And we saw if a node tries to act maliciously, then all their hashes are going to be way out of whack and they're not going to match everybody else. This gives blockchains this incredibly potent immutability trait where nothing can be changed or corrupted. So in essence, we can think of a blockchain as a decentralized database. And with Ethereum, it has an extra additional feature where it also can do computation in a decentralized manner. Now let's talk consensus, proof of work, and proof of stake, because you've probably heard these before and they're really important to how these blockchains actually work. When we went through that blockchain example and we did that mining feature, this is what's known as proof of work. Proof of work and proof of stake fall under this umbrella of consensus. And consensus is a really important topic when it comes to blockchains. Consensus is defined as the mechanism used to reach an agreement on the state or a single value on the blockchain, especially in a decentralized system. I briefly alluded to this consensus mechanism in our blockchain example when I said if one changes something and the other two don't, then majority will rule and kick that one out. This is part of that consensus mechanism. Now, very roughly, a consensus protocol in a blockchain or decentralized system can be broken down into two pieces: a chain selection algorithm and a Sybil resistance mechanism. That mining piece that we were doing, or the proof of work algorithm, is what's known as a Sybil resistance mechanism. And this is what Ethereum and Bitcoin currently use. Please note that depending on when you're watching this, if ETH2 is out, then it's no longer proof of work. Now, proof of work is known as a Sybil resistance mechanism because it defines a way to figure out who is the block author. Which node is going to be the node who did the work to find that mine and be the author of that block, so all the other nodes can verify that it's accurate. Sybil resistance is a blockchain's ability to defend against users creating a large number of pseudo-anonymous identities to gain a disproportionately advantageous influence over said system. And in layman's terms, it's basically a way for a blockchain to defend against somebody making a bunch of fake blockchains so that they can get more and more rewards. Now, there are two types of the Sybil resistance mechanisms that we're going to talk about here, namely proof of work and proof of stake. Let's talk about proof of work a little bit more in depth first. In proof of work, this is Sybil resistant because a single node has to go through a very computationally expensive process called mining, which we demonstrated earlier, to figure out the answer to the blockchain's riddle of finding that correct nonce or whatever the blockchain system has in place. In proof of work, this works because no matter how many pseudo-anonymous accounts you make, each one still has to undergo this very computationally expensive activity of finding the answer to the proof of work problem or the proof of work riddle, which again, in our demonstration, it was finding a nonce with that first 4 zeros. But again, each blockchain might change the riddle or change the problem to be a little bit different. In fact, some of these blockchains make this riddle intentionally hard or intentionally easy to change what's called the block time. The block time is how long it takes between blocks being published, and it's proportional to how hard these algorithms are. So these problems actually can change depending on how long they want the block time to be. If a system wants the block time to be very, very long, they just make the problem very, very hard. If they want it to be very short, they make the problem a lot easier. We'll talk about Sybil attacks in a little bit and how they can affect the system. But with proof of work, it's a verifiable way to figure out who the block author is and be Sybil resistant. Now, you need to combine this with a chain selection rule, create this consensus. Now, there's some consensus protocols that have more features, but very, very roughly, these are the two pieces that we're going to look at. The second piece is going to be a chain selection rule. How do we know which blockchain is actually the real blockchain and the true blockchain? Now, on Bitcoin and Ethereum, they both use a form of consensus called Nakamoto consensus. And this is a combination of proof of work and longest chain rule. The decentralized network decides that whichever blockchain has the longest chain or the most number of blocks on it is going to be the chain that they use. This makes a lot of sense because every additional block that a chain is behind, it's going to take more and more computation for it to come up. That's why when we saw in our transaction, we actually saw confirmations. The number of confirmations is the number of additional blocks added on after our transaction went through in a block. So if we see confirmations as 2, it means that the block that our transaction was in has 2 blocks ahead of it in the longest chain. Now, I do want to point out that a lot of people use proof of work as a consensus protocol, and I do want to say that this is a little bit inaccurate, but sometimes people use it interchangeably. Proof of work is a piece of the overall consensus protocol, which in Bitcoin and Ethereum 1's current case is Nakamoto consensus. Nakamoto consensus is a combination of proof of work and this longest chain rule, both equally and very, very important. Now, proof of work also tells us where these transaction fees and these block rewards go to. Remember how when we made this transaction, we had to talk about gas and a transaction fee. So who's getting paid? Who is getting this transaction? And this transaction fee is going to the miners or the validators. In a proof of work network, they're called miners, and in the proof of stake network, they're called validators. They are a little bit different, and we'll get into that when we talk about proof of stake. In this proof of work system, all these nodes are competing against each other to find the answer to the blockchain riddle. Remember, in our example, it was to find a hash that has 4 zeros at the start. And again, depending on the blockchain implementation, that riddle is going to be a little bit different. but all the nodes are trying as many as possible to try to get this answer first. Why? Because the first node to figure out the answer to the blockchain riddle is going to get that transaction fee. They're going to get paid from that. Now, when a node gets paid, they actually get paid in two different ways. One is going to be with a transaction fee, and another piece is going to be the block reward. Remember how we talked about alternating the gas price or the GUI on our transaction? Well, that's the transaction fee that we're going to pay to these blockchain nodes for including our transaction. The block reward is given to these nodes from the protocol, from the blockchain itself. You've probably heard of the Bitcoin halving before. The halving is referring to this block reward getting cut in half, and it's supposed to be cut in half roughly every 4 years. This block reward increases the circulating amount of whatever cryptocurrency that is being rewarded. For example, on Ethereum, the block reward is giving out Ethereum, and on Bitcoin, the block reward is giving out Bitcoin. So these nodes are competing against each other to be the first one to find this transaction, to be the first one to find the answer to this problem, so that they can be the ones to win both this block reward and your transaction fee. Some blockchains, like Bitcoin for example, have a set time when they're no longer going to give out block rewards, and the miners or the nodes are only going to get paid from transaction fees. Now, this gas fee, again, is paid by whoever initialized the transaction. When we got our funds from the faucet, there was some server and somebody else was paying the transaction fee for us. However, when we sent Ether from one account to another, our first account actually paid some transaction fee to send that Ether. In proof of stake, there's also a gas fee, but it's paid out to validators instead of miners, and we'll talk about that in a little bit. Now let's talk about two types of attacks that can happen in these blockchain worlds. Let's talk about the first one being the Sybil attack. The Sybil attack is when a user creates a whole bunch of pseudo-anonymous accounts to try to influence a network. Now, obviously, on Bitcoin and Ethereum, this is really, really difficult because the user needs to do all this work in proof of work or have a ton of collateral in proof of stake, which again, we'll talk about in a bit. The other more prevalent attack is what's known as a 51% attack. Now, as we saw as part of our consensus protocol, these blockchains are going to agree that the longest chain is the one that they're going to go with, so long as it matches up with 51% of the rest of the network. This means that if you have the longest chain and you have more than 51% of the rest of the network, you can do what's called a fork in the network and bring the network onto your now longest chain. Now, Sybil attacks obviously are when a single node or a single entity tries to affect the decentrality of the network by pretending to be multiple different people, although they're just the same person or entity. And like I said, it's really difficult to do in proof of work and proof of stake. So you can see now that blockchains are very democratic. Whichever blockchain has the most buy-in and is the longest is the blockchain that the whole system is going to corroborate. When nodes produce a new block and add it to the longest chain, the other nodes will follow this longest chain that the rest of the network is agreeing with, add those blocks to their chain, and follow up. So very small reorganizations are actually pretty common when a blockchain picks a block from a different longest chain, puts it on, and then has to swap it out for another block and continue with a different blockchain. However, if a group of nodes had enough nodes or enough power, they could essentially be 51% of the network and influence the network in whatever direction that they wanted. This is what's known as a 51% attack, and it's happened on blockchains like Ethereum Classic, which is not Ethereum. This is why the bigger a blockchain is, the more decentralized and the more secure it becomes. So after you watch this video and you become a blockchain engineering expert, I definitely recommend you run a node as well, because you are going to increase the security of the network as a whole by running a node. So proof of work is fantastic because it allows us to very easily protect against these Sybil attacks and keep our blockchains decentralized and secure. However, it has some drawbacks as well. Proof of work costs a lot of electricity because every single node is running as fast as they can to win this race to get the rewards. This leads to, obviously, an environmental impact. Now, since proof of work and Nakamoto consensus, a lot of other protocols have taken this idea and gone in a different direction with a different Sybil resistance protocol. A lot of them with the intention to be a lot more environmentally friendly. And the most popular one right now is proof of stake. There are some chains that are already using this proof of stake protocol and that are live and thriving. Some of them are like Avalanche Solana, Polygon, Polkadot, and Terra. And additionally, Ethereum has decided to upgrade to ETH2, which will have this proof of stake algorithm as well. It'll also have some other features which we'll talk about in a bit. Now, as a quick aside, all the tools that we're going to learn here are still going to work in ETH2. So depending on when you watch this, everything here is still valid. So let's talk about proof of stake now. Again, this is a different Sybil resistance mechanism. Instead of solving this difficult problem, proof of stake nodes put up some collateral that they're going to behave honestly, aka they stake. In the example of Ethereum 2, nodes put up some Ethereum as a stake that they're going to behave honestly in the network. If they misbehaved in the network, they are going to be slashed or removed some of their stake. Obviously, this is a very good civil resistance mechanism because if you try to create a whole bunch of anonymous accounts, then each one of those accounts, you have to put up some stake. And if you misbehave, you're going to run the risk of losing all the money that you put up as collateral. In this system, miners are actually called validators because they're no longer binding anything. They're actually just validating other nodes. Now, unlike proof of work, which every node is racing to be the first one to find the block, in proof of stake, nodes are actually randomly chosen to propose the new block. And then the rest of the validators will validate if that node has proposed the block honestly. As we saw with our cryptography lesson, it's usually very easy for other nodes to verify if a proposal or a transaction is honest. Now, randomness is a really important topic when we're talking about blockchains, because keep in mind, these blockchains are deterministic systems. They're walled gardens from the rest of the world. And as you know, a deterministic system, by definition, can't have random numbers. So how do we choose the random validators in the system? Well, it changes from blockchain to blockchain, and actually choosing the node will change blockchain to blockchain. But in ETH2, they're using what's called RANDAO, at least for the original implementation. This is a decentralized autonomous organization that collectively chooses the random number and collectively chooses which node is going to run next. We aren't going to dive too deep into this because there's a good chance that this might change in the future. But we will go into randomness solutions in blockchain later on in this course. Now, proof of stake obviously has some pros and cons as well. Pros are that, again, it is a great civil resistance mechanism and a great way to figure out who the author of a block should be. The other pros are that it's way less computationally expensive to figure out the new block, because instead of every single node on the network trying to do this, only one node needs to do this. And then the rest of the nodes just need to validate it. The cons are that it's usually considered a slightly less decentralized network due to the upfront staking costs it costs to participate. Now, this gets into a little bit of a philosophical battle on how decentralized is decentralized enough, and I think that's up to the community to decide. And as we progress, I think we'll learn more and more about how decentralized is decentralized enough. The general consensus amongst blockchain engineers, though, is that proof of stake is very, very decentralized and very secure. This massive environmental impact improvement is one of the two main reasons why ETH is shifting to ETH2. It reduces the environmental impact by up to 99%. Now, these are the main pieces of proof of work and proof of stake, but I did want to talk about another concept that's really important in these ecosystems, and that is scalability. When we were talking about gas prices, we were saying that the gas prices can get really high if a lot of people want to send a transaction, because a block only has so much block space and the nodes can only add so many nodes. So when a lot of people want to use a blockchain, the gas price skyrockets. This is not very scalable because if we want to add more and more people to these blockchains, it's going to cost more and more to use the blockchains because more people are going to want to get into these blocks. This means that there's kind of a ceiling to how many people can use the system because of the financial constraints that'll get imposed as gas prices keep rising. Ethereum 2 is not only attacking the environmental impact of proof of work by switching to proof of stake, but they are also implementing this new methodology called sharding. And sharding is a solution to this scalability problem. A sharded blockchain really just means that it's going to be a blockchain of blockchains. There is a main chain that's going to coordinate everything amongst several chains that hook into this main chain. This means that there's more chains for people to make transactions on, effectively increasing the amount of block space that there is. Sharding can greatly increase the number of transactions on a blockchain layer 1. Now, there's another term that might be the first time you heard it, a layer 1. We're going to talk about layer 1s and layer 2s in terms of scalability really quickly as well. A layer 1 refers to any base layer blockchain implementation. Bitcoin's a layer 1, Ethereum's a layer 1, Avalanche is a layer 1. These are the base layer blockchain solutions. A layer 2 is any application that is added on top of a layer 1, added on top of a blockchain. Some examples of layer 2s are going to be Chainlink, Arbitrum, or Optimism. Arbitrum and Optimism are very interesting because they are layer 2s that also look to solve this scalability issue. Arbitrum and Optimism are what's known as rollups, and they roll up their transactions into a layer 1, like Ethereum. We're not going to go too deep into rollups and how they actually work, but all you really need to know is that a rollup is kind of like a sharded chain. They derive their security from the base layer, from the layer 1, like Ethereum, and they bulk send their transactions onto the layer 1. They solve some of the scalability issues by being another blockchain that people can make transactions on, still on kind of this base Ethereum layer. Now, they're different from sidechains because sidechains derive their security from their own protocols. Rollups derive their security from the base layers. So Arbitrum and Optimism, for example, is going to be just about as secure as Ethereum. There's some fantastic guides in there that go a little bit deeper into rollups, and I've left a link in the description for you. All right, so we just talked about a lot of stuff. So let's do a quick recap before moving on. Ethereum and Bitcoin are currently both proof-of-work blockchains that follow Nakamoto consensus. However, Ethereum is moving to Ethereum 2, which will be a proof-of-stake sharded blockchain. Sybil attacks are prevented due to protocols like proof-of-work and proof-of-stake. 51% attacks grow increasingly harder with the size of blockchain, so you should run a node. Consensus is the mechanism that allows a blockchain to agree upon what the state of the blockchain is. Sharding and rollups are solutions to scalability issues on layer 1s. A layer 1 is any base blockchain implementation, like Bitcoin or Ethereum. A blockchain scalability problem is that there's not always enough block space for the amount of transactions that want to get in them. This leads to very high gas prices. And again, gas prices are how much it costs to interact with a blockchain. Whew.
So that's it for the blockchain basics and the blockchain explainers. With just this information, you now can go off into the world and start working with blockchains and interacting with blockchains with at least some level of knowledge as to what's going on. You should be incredibly proud of yourself for just making it this far. Definitely be sure to give yourself a pat on the back and a round of applause. Now that we've gotten a lot of the basics and the fundamentals out of the way, let's start jumping into the coding aspect. This is where you're going to learn how to actually build these smart contracts, how to build these trust minimized agreements in these blockchains and in these smart contract platforms. This next section, this Solidity Basics, the Solidity Fundamentals section, will give you all the skills to start actually coding Solidity and understanding how these smart contracts work underneath the hood. So at this point, absolutely give yourself a high five, maybe say hi in the GitHub discussions, maybe say hi in the community on Twitter, on Reddit, etc., and be proud of just making it this far. The journey has really only just begun, but you've already learned so much. Let's begin the next section and let's jump into the code.